Hello everyone. We are starting our lecture now on chapter 12, which is on inferences for population proportions. So far we have been working with means, right? The one population mean or two population means. This time we are going to go to a different kind of metrics. It's called proportions. All right. And proportions translates to percentage. So the data that's going to be presented to us is either as a proportion, a value between 0 and 1, or in percentage form. And this applies um, to surveys which answer the question as yes or no. Okay, so we'll go into the details of this. This is just an introduction and the title page. Let's go into the next few slides to see what exactly we will cover, and then we'll go into the details of it. So in this chapter, we'll first start with finding confidence intervals for one population proportions and then performing a hypothesis test for one population proportion. And finally, we'll learn how to compare two population proportion. Again, just keep in mind that here we do not see the word mean mentioned anywhere. It's all about proportions. All right. So we will first go through some concepts behind proportions, and then we will go into how to perform the inferential studies. Let's talk about the population proportion and sample proportion. Just like we had population mean and sample means, we talked about them in the previous chapters. For this study, we will only talk about proportions, so it'll be population proportion and sample proportion. So it says here, consider a population in which each member either has or does not have a specified attribute. Then we use the following notation and terminology. The population proportion is represented by the lowercase letter p, and it is the proportion or percentage of the entire population that has the specified attribute. And the sample proportion, on the other hand, has p and a hat symbol over it, and it is the proportion or percentage of a sample from the population that has a specified attribute. Now, what do we understand by a specified attribute? Now, in these kind of studies, our study is looking for a specific characteristic that the sample is supposed to meet. All right. So let's say, for example, we want to assess um, the what what percentage of students pass a course. Okay, pass a course. So that is the specific attribute we are looking for in our study. We want to determine what is the percentage of pass in a particular course, maybe statistics or calculus or whatever it may be. So the attribute that we are looking for is passing the course. So when I send out my survey to my students, the question presented to them is, did you pass the course? And I'm looking for what or how many students responded as yes. If they have responded to the question as yes, they have met the specified attribute. So in this particular study, in this example, the specified attribute would be regarded, the specified attribute would be passing the course. Passing the course. And whoever or however many students have met this particular attribute, this particular characteristic, will be considered as a success. That means we have obtained a response which was a yes to passing the course. That means we obtained a success. All right, somebody met that particular characteristic, or a certain percentage of students met the particular characteristic. So we'll go further into it. We'll talk about how to calculate the proportion from the yes responses and so on in the next few slides. As in the study of means, in the study of proportions also we work with samples, because the population is so large, it's not feasible to work with the entire population. So we draw a sample, a representative sample from our population. Okay, so the sample proportion, denoted as P hat, is calculated using this formula here, x divided by n. So what is x? X is the number of people who have met the specified attribute we have been looking for. So where x denotes the number of members in the sample that have the specified attribute. So the number of respondents who said yes to your question. And as usual, n denotes the sample size. So n stands for the sample size, and x denotes the number of members that have met the specified attribute we have been looking for. So x divided by n. Again, another thing I want to mention here is x divided by n is going to be very similar to some of the previous formulas we have learned for relative frequency. Remember, relative frequency was f over n, right? This is similar to it, except that here x represents the number of people who meets a specified attribute. Not just people, it could be any items or any members. Okay, so x divided by n, it's going to give us a ratio value between 0 and 1. Here we talk a little more about sample proportions. Again, the formula is P hat equals x divided by n, where x represents the number of members in the sample with the specified attribute. Number of people who responded yes to the question that you had circulated. Also, it refers to, or it is referred to as, the number of successes. When somebody meets the specified attribute, it is referred to as successes. Now, if x is the number of members out of n members that have met the specified attribute, that is the successes, then the number of members that did not meet the specified attribute can be calculated using the formula n minus x, right? So we have a total, okay, a total of n members. We have a total of n members, out of which x met the attribute, correct? X number met the attribute. So to find out how many did not meet the attribute, all you have to do is n minus x, correct? Now, likewise with proportions, if we know that p hat is the proportion of members that meets the attribute, if it represents the proportion of sample members meeting the attribute, meets the specified attribute, then the proportion not meeting attribute would be, the attribute can be found easily by the formula 1 minus p hat. So you don't have to be explicitly given the number of people who did not meet the specified attribute or the proportion of people that did not meet the particular attribute. If you know x, if you know n, you can find the proportion of members that meets the attribute, and then from there you can calculate the proportion of members not meeting the attribute by just doing 1 minus p hat. All right, that will give you the proportion not meeting the attribute. However, if the question says how many members did not meet the attribute, then you have to do n minus x. Now, to show you the correspondence between the notations for means and proportions, the notation for means at the parameter level, that means population level, the metrics associated with population is referred to as parameter, whereas the metrics associated with samples is referred to or are referred to as a statistic. So when we talk about means and we talk about the population mean, we use the Greek letter mu, and if we are referring to the sample mean, it's x bar. Okay, it's x with a bar over it. As far as proportions are concerned, when we refer to the population proportion, we just use the lowercase p in italicized form. And if we are referring to the sample proportion, then it's p with a hat over it. And make sure that you do not mix up these two notations between the population proportion and the sample proportion, because you will need to make sure that you use the correct notation when stating your hypothesis and so on. We'll now talk about an example that we'll introduce here in this lecture, but when we will solve this problem, we will work out this example later on in a worksheet similar to what I did with the previous chapters. All right, so let's get introduced to this particular example and go through some of the basic understanding of it. Right, it says here a survey polled 1,010 randomly selected US employees. A proportion of the 1,010 employees sampled who played hooky was used to estimate the proportion of all US employees who play hooky. Discuss the statistical notation and terminology used in this. Let me just explain what playing hooky is. Playing hooky means that if somebody calls in sick, somebody who is not really sick, but they call in sick at work, but just to have a day off. All right, they are not really sick, but they just call in sick because they want to stay home. They just don't feel like going into work. That's what playing hooky is. So maybe the labor department wanted to survey and on people's productivity, and they wanted to see what proportion, what percentage of all US employees play hooky. All right. So the total number of people sampled for this study was 1,010. So that's our N, right? N represents sample size. So N equals 1010. They haven't told us how many of these individuals that were surveyed responded with yes, how many met the specified attribute that they played hooky once in a while. Okay. However, in this part of the question, it says just discuss the statistical notation and terminology used in this. So for population proportion, P represents, P without the hat, which is the population proportion, represents the proportion of all US employees that play hooky, and that's the parameter, that's the metrics associated with the population. So at this point, they're not asking us to do any calculations. They're just making sure that we understand how to represent this particular example as population, what part represents the population proportion versus the sample proportion. So population means entire group of US employees, all US employees. So you will see often that population is mentioned as all US employees or all uh, students or all men or all women. So the word all will be included in the population mean or population proportion whenever we refer to a population. The sample proportion represented by P hat is the proportion of the 1010 US employees or samples that play hooky. So out of a total of all US employees, which could be in millions, several hundred millions, uh, a sample of only 1010 were selected, randomly selected, and to whom the survey was sent out asking whether they played hooky or not. Okay. Now we will go into talking a little bit about the sampling distribution of the sample proportion. Now, before we go into any study, especially inferential study, we have to identify how the sampling distribution is. And sampling distribution means we talk about the mean. We try to understand how the population mean is related to the mean of all the sample means. Now, here we are talking about population proportion. So we are going to refer to it as the mean of all sample means will be equal to whatever the population proportion is. All right. And that is going to be analogous to what we had studied previously when we were doing the one mean hypothesis test. If you remember, we said about the distribution of one mean hypothesis test that the mean of all the sample mean is always equal to the population mean. Now, this is something that actually was studied in or was taught in not chapter 7, it would be in statistics 1, in a chapter in statistics 1. All right. So you may just have to recall it, or if you are reading the book, then you can look back on chapter 7. All right. This should be there in chapter 7. The mean of all the sample mean is equal to the population mean, and then the standard deviation of all the sample mean will be equal to the standard population standard deviation divided by square root over n, and of course it would be a normal distribution, but this one was for one mean uh, inferential studies. All right, one mean confidence intervals and one mean uh, hypothesis tests. When we are working with proportions, all right, we are going to say it the mean of all sample proportions. Mean of all sample proportions is equal to the population proportion. Look at this P, it's without a hat. So that represents the population proportion. That is, the sample proportion is an unbiased estimator of the population proportion. That's how we say it, in other words. The standard deviation of the sample proportion. All right. So in chapter 12, we are only referring to proportions, no more means. All right. So the standard deviation of sample proportion equals the square root of the product of the population proportion and 1 minus the population proportion divided by the sample size. So this is how it's going to look like. Sigma of p hat, that means the standard deviation of the proportions, is equal to square root over p times 1 minus p divided by n. So p represents our success proportion. That is multiplied by the failure proportion. Remember, we said that our success proportion will be represented by P. That's the success proportion. To find the failure proportion, all you need to do is subtract the P from 1. So that would be 1 minus P. And in the formula for the standard deviation, it's square root over P times 1 minus P divided by the sample size N. And finally, about the distribution P hat, that means the sample proportion is approximately normally distributed for large n. That means when n is greater or equal to 30. Okay, so it says here in this bubble, if n is large, the possible sample proportions for samples of size n have a normal distribution with mean of p, and this is the population proportion, and the standard deviation square root over p times 1 minus p. This should be division, all right? I see that that's missing. There should be a division sign between p times 1 minus p divided by n. Okay? Let's look at this question on the sampling distribution of the sample proportion. It says, suppose that 19.1% of all employees play hooky, that is, that the population proportion is P equals 0.191. So 19.1% of all employees, this word itself tells us that they are referring to the population proportion, all right? So even if they hadn't told us this, if they had left out this that is part where they have explained it is the population proportion, we should have been able to figure out by seeing this word all employees that they are referring to the population proportion. All right, so P equals 0.19. Where did they get 0.191 from? From this percentage. They converted this to decimal. All right, 19.1 divided by 100 gives us 0.191, and that is the population proportion. Then for samples of size 1010, the variable P hat, which is the sample proportion, is approximately normally distributed with mean. Remember, the rule is that the mean of all sample proportions, of all possible sample proportions, will be equal to whatever the population proportion is. In this case, it is 0.191, so we can say that it's going to be 0.191. And the standard deviation will be found using this formula, square root over P multiplied by 1 minus P. So we know what P is, 0.191. 1 minus P, which is the failure proportion, needs to be calculated and then divided by n. All right, n being 1010s. And once we take the square root of that, we come up with a value of 0.012. All right, that is the standard deviation of all sample proportions, all possible samples is what it means. All right, and it'll be normally distributed, which they've already stated here. Now that we have talked about the sampling distribution, Let's go into how to find the confidence interval. Now, the good thing about proportions is that we use the Z distribution, all right, for all inferential studies using proportions, all right. So one proportion Z interval procedure. The purpose is to find a confidence interval for a population proportion P. Assumptions, simple random sample. So of course the sample has to be selected randomly. And number two, the number of successes x and the number of failures n minus x should both be greater or equal to 5. So these are the two assumptions that need to be satisfied for us to be able to use the Z interval procedure. The broad steps are the same. The only difference will be the formula that we will be using to find the confidence interval. So step one is for confidence level of 1 minus alpha, use the table or your graphing calculators to find Z of alpha by 2. Right now, we always have to divide alpha by 2 when we find confidence intervals. Step 2 is finding the confidence intervals using the formula. There's a minus to be done and a plus. And here you see this is the formula for the standard deviation. So you find your sample proportion and to that you add and subtract Z of alpha by 2 multiplied by square root over P hat times 1 minus P hat divided by n. This was the formula that we learned when we were talking about this sampling distribution. Well, in the sampling distribution, we use the population proportions, the P instead of P hat. But when we find the confidence interval, we will use the P hat values, where Z of alpha by 2 is found in step 1 and is the sample size, and P hat can be found by dividing X, that means the number of um, successes, the number of yes to our question, right, divided by n. That's the sample proportion, and in step 3 we interpret the confidence interval. So let's work this problem on finding the one proportion Z interval procedure. I'm going to work this out anyway in a worksheet as well, but it doesn't hurt to go over it in this lecture as well. So it says playing hooky from work. A poll was conducted on 1010 randomly selected US employees. All right, it should say here conducted. Was conducted on 1010 randomly selected US employees. The employees sampled were asked whether they play hooky, that is, call in sick at least once a year, simply to relax at home. Now, 202 responded yes. So 202 members met that specified attribute. That was the success. Use this data to find a 95% confidence interval for the proportion P of all US employees who play hooky. All right. So the first step is to note down the data n and x, because we are going to use those values to calculate our proportions. So n is 1010, correct? This is n. This represents our n. X will represent the number of respondents who said yes. So that's 202. So I'm going to write 202. Next, it says calculate the proportions of success, that is those who played hooky once a year. So that would be x over n. So keep in mind the formula for P hat. Here we are calculating the sample proportion. So P hat equals x divided by n. So P hat will be equal to 202 divided by 1010, and that comes to 0.20 approximately 0.20. So we can write here p hat equals 0.20. 0.20. Next, it says calculate the proportion of failures, that is those who don't play hooky. Now, once you have calculated your p hat value, which is 0.20, all you must do is subtract it from 1 to get the failures. So it would be 1 minus p hat, which is 1 minus 0.20, which is 0.80. In other words, 20% of the people surveyed said they played hooky and 80% said they do not play hooky. However, when we talk about proportions, it's 0.20 for the success proportion and 0.80 for the failure proportion, those who did not meet the specified attribute that we were looking for. Now keep in mind, always remind yourself that the proportion has to be a value between 0 and 1. All right, if you are getting a value which is negative, or if you're getting a value which is greater than 1, then there is a problem in your calculation. You have to go back and check your calculation, right? Now here we will go through the steps of finding the confidence interval. We are using the 95% confidence interval to build the confidence interval. So it says state CI, so that's going to be 95%. Confidence level is the decimal version of the percentage confidence interval, so that's 0.95. And alpha is 1 minus whatever CL is. All this should be revision for you. So 1 minus 0.95 is 0.05, and for confidence intervals we always divide alpha by 2, which is 0.025. Let's quickly draw a picture here of what we are looking at. We have our normal curve. All right, this is our normal curve, and the center point is going to be our p hat. In this case, we are working with proportion, so our point estimate, which is the center point around the interval, is going to be whatever p hat value we found. In this case, that's going to be 0.20. That was our sample proportion, correct? And then what is alpha by 2? Alpha by 2 represents the area outside each of the endpoints of the interval. That means if at the lower end point, if I extend this, all right, the area outside the interval is going to be 0.025, which is alpha by 2. And the same thing on the other side, this area is also going to be 0.025 alpha by 2. We divided alpha into 2 equal parts. Right? So to find the endpoints, all we need to do is find z of 0.025 and then convert that to the corresponding x bar value. All right, so this is going to be negative z of 0.025. But our good thing about working with the z distribution is that we don't have to worry about DFs, degrees of freedom, and all that, correct? So on the right hand side, it will be z of 0.025, positive z of 0.025. So if we go back to our table, we will see that z of 0.025 is equal to 1.96. All right. You can look it up from the table or from your graphing calculators if you have one. So now we have to apply the formula for the confidence interval to find the end points, all right, the proportion values at the end points. So the formula is p hat, which is our point estimate, which is 0.20, right? That's our point estimate, the sample proportion, plus minus z of alpha by 2 is 1.96, 1.96 multiplied by the square root, over p hat is again 0.20 multiplied by 1 minus p hat, and we found out in the previous slide that 1 minus p hat is 0.80, so 0.80, right? 1 minus 0.2 is 0.8 divided by n, which is 1010, all right? So 1010, again, it's division, it's not multiplication. So keep that in mind, don't make that mistake. So this whole expression here, the 1.96 times square root over 0.2 times 0.8 divided by 1010 represents the margin of error, all right, the error that we are adding and subtracting to the point estimate value of 0.2. All right, so once we do the calculations, we should come up with a value for the end points, which is 0.175 to 0.22. All right, you can run your calculators through this for the calculated value. So 0.1725, 0.175 is the lower end of the interval, and 0.22 is the upper end of the interval. Okay, and after that, once you find your intervals, you have to interpret it correctly, and the way we interpret it is we can be 95% confident that we can be 95% confident that the proportion, okay, the proportion P, you can just use the verbiage from the question itself, proportion P of all US employees playing hooky will be contained in the interval 0.175 to 0.22. All right, so that's the correct way to interpret it. Next, we go through the margin of error formula, which we've already used in our calculation for the confidence interval, but just reviewing it, it's E equals Z of alpha by 2 multiplied by square root over P hat times 1 minus P hat divided by N. All right, so the margin of error we found in our problem that we added and subtracted to our point estimate was 0.024. Now do that calculation separately. I don't think in the previous slide I showed that this calculation, but I leave it to you, and just perform the calculation for the error and note it separately, all right, instead of doing everything at once to find the endpoints. It'll be much easier for you to break it up. Okay. Now there's another question we sometimes have to answer, which is on finding the sample size to maintain a certain margin of error and a particular confidence interval. All right, we did a similar problem for means. All right, in chapter 8, when we were studying confidence intervals, we also worked on a formula to find the sample size for a given margin of error and for a given confidence interval. So the same thing here, but we are dealing with proportions at this point. So uh, the formula is a little bit different. It says here a 1 minus alpha level confidence interval for a population proportion that has a margin of error of at most E can be obtained by choosing N equals 0.25 times Z of alpha by 2 divided by E whole squared. Okay, rounded up to the nearest whole number. Now this 0.25 is a hard-coded value. It's a constant value, right? It's a constant value, but it comes from the fact that P hat is being assumed as 0.5 and 1 minus p hat. Therefore, if p hat is 0.5, then 1 minus p hat is going to be 0.5 as well. And when you multiply the two, you'll end up with 0.25. All right, so that's where the 0.25 is coming from. This whole formula is actually derived from the margin of error formula. The margin of error formula, if you recall, was E equals, what was it? Z of alpha by 2 times square root over P hat times 1 minus P hat divided by N, correct? That was the formula for margin of error. If you solve this formula for N, you will come up with this formula for N, all right? Uh, the only problem is we do not know what p hat is going to be, because this p hat is in the formula. We don't know what p hat should be, and therefore we have to use an estimated value. All right, sometimes we can use 0.5. We can assume that p hat is 0.5. Therefore, 1 minus p hat is also going to be 0.5. And when you multiply the two, all right, in this formula, like over here, you will get 0.25. That's where that 0.25 comes from. Now, if you can make an educated guess as to what the p hat value is going to be for the observed value of p hat, then we can use that guesstimated value. All right. But most of the time we will be using an unguessed value. We will just assume that p hat is 0.5 and we will use the 0.25 constant value in our formula. Also, if you have in mind a likely range for the observed value of p hat, then you should apply the preceding formula with the educated guess for the observed value of p hat being the value in the range closest to 0.5. Don't worry about this last part. Just keep in mind that if your question asks you to use value without guessing the proportion, then use this formula. If they tell you, if they give you a guessed proportion value, all right, then you will use this formula, all right? We'll now get started with chapter 12.2, which is on hypothesis tests for one population proportion. So we will just go through the steps of performing a hypothesis test, and then I will use my worksheets to explain the step-by-step procedure. We'll work through an example, but here we will just introduce the problem that we are going to work in our worksheets, right? Now, the hypothesis test we are going to use for proportions is the z-test procedure. So we are going to use the z-distribution for hypothesis tests as well, just like we did for the confidence interval. So the z-distribution means we don't have to worry about degrees of freedom, and we have the complete table available to refer to when we find the z values or the alpha values. Now, the one proportion z-test is for the performance of a hypothesis test. The assumptions are that it must be a simple random sample, and number two are both n times p sub 0 and n times 1 minus p sub 0 are 5 and greater. What is p sub 0? P sub 0 is the proportion stated in the null hypothesis statement. So the way we state our null hypothesis, it should say H sub 0 colon P equals P sub 0. P sub 0 again is the null hypothesis proportion. Because it's a one proportion test, it should have a specific value between 0 and 1. And the alternative hypothesis will be stated in one of these three ways. It could either be a two-tailed test, therefore P not equal to P sub 0, or H sub A colon P less than P sub 0, in which case it will be a left tail test, or H sub A colon P greater than P sub 0. In that case, it's a right tail test. In step 2, we have to decide on the significance level alpha. In step 3, we have to, of course, compute our test statistic using the formula p hat minus p sub 0 divided by the standard deviation formula for proportions, which is square root over p sub 0 times 1 minus p sub 0 divided by n. So this corresponds to the formula that we used for our one population mean. The only thing that's different is that instead of x bar minus mu, we use p sub p hat, which is the sample proportion minus the null hypothesis proportion, divided by the formula for the standard deviation of proportions. And please note here, with under the radicals, we have p sub 0, which is again the null hypothesis proportion, whatever will be stated for the null hypothesis. Okay, and then in step 4, we perform the test using these approaches, the critical value or the p-value or both. And then step 5, we take a decision based on what we get from step 4. And then step 6, we have to interpret the results in the context of the problem. All right. This is an application-based example that we are going to work through our worksheet. But let's just introduce the example here and discuss some basic facts, discuss the data in this as part of this lecture. The problem is on economic powerhouse. A national poll of 1,015 randomly selected US adults asked which country is the leading economic power in the world. Of those sampled, 538 said China. At the 5% significance level, do the data provide sufficient evidence to conclude that a majority, which means greater than 50%, believe China is the leading economic power? All right. So a sample of 1,015 US adults were surveyed. So the sample size here is 1,015, which I'm going to write over here next to n, 1015. All right, they were asked which country is the leading economic power, and 538 of the respondents said that China was the leading economic power. Now the question says, at the 5% significance level, do the data provide sufficient evidence to conclude that a majority, which means greater than 50%, responded China being the leading economic power. Now this question here, when it says note down the data, this P sub 0 is not P hat. Keep that in mind. All right. P hat is the sample proportion. P sub 0 refers to the null hypothesis proportion. The null hypothesis proportion, just like H sub 0 refers to the null hypothesis and mu sub 0 refers to the null hypothesis mean, the P sub 0 refers to the null hypothesis proportion. So based on this question, what would the null hypothesis proportion mean? It would be a proportion that represents majority, that is greater than 50%. So for proportion, you cannot put 50%. It has to be a value between 0 and 1. So you have to convert the percentage to proportion to decimal, and it's going to be 0.5. That's what the that's what the null proportion is. All right. The P hat, on the other hand, is X divided by N. So X here is the number of people who said China. So 538 divided by 1015, whatever that comes to, get whatever that calculates to is going to be our P hat. Assumptions. The first assumption is that it has to be a simple random sample, and then secondly it says both n times p sub 0 and n times 1 minus p sub 0 must be greater or equal to 5. All right, so p sub 0 is 0.5, so 0.5 times 1015. All right, p sub 0 is 0.5. 0.5 times 1015 is definitely greater than 0, and 0.5 1 minus p sub 0 is also 0.5, so that times n will also definitely be greater than 0. So both conditions are met, both assumptions are met. Next it says state null and alternate hypothesis. So your null hypothesis should be written as H sub 0 colon, not mu, but P. All right, P without the hat, because it has to be stated in terms of parameters, population metrics. All right, so we have to say P equals, null hypothesis always has the equal sign in it, and then P equals 0.5. All right, whereas the alternate hypothesis is going to say P is, it says majority, right? Greater than 50. So greater than 0.5. So that's our null and alternate hypothesis stated for this problem. And decide on the significance level, it says 5%. So alpha is going to be 0.05. Now, the alternate hypothesis says P is greater than 0.5. So what kind of tail test is this? This happens to be a right tail test. If it's a one tail test, a right tailed or a left tail test, we do not need to split our alpha. Alpha would stay at 0.05. Now, in the previous slide, we did the first two parts of a hypothesis test where we stated our null and alternate hypothesis, and we also determined our significance level, which comes from whatever significance level we are asked to perform the test at. From the significance level, we derive the alpha value, right? So alpha is the decimal version of this 5%, which is 0.05. Now, uh, in the third step, the third step now is where we compute our test statistic or the evidence that we present as a rebuttal to the null hypothesis, right? And the formula for proportions, the formula is p hat, which is the sample proportion minus the p sub 0, which is the null hypothesis proportion, divided by the formula in the denominator is that of the standard deviation of proportions, right? So p hat is the sample proportion calculated from the data given to us. P hat equals x divided by n. That's the formula. X represents the number of respondents that said China was the super economic power. That 538 divided by n is the total number of people who were polled. That's 1015, and that gives us a value of 0.53. So that's our p hat. So let's plug in the values. Z sub 0, the test statistic is often represented as Z sub 0 or T sub 0 and so on. So p hat is 0.53 minus p sub 0 is the 50%, the break-even point, all right? So it's going to be 0.5. That's what we use to state our null hypothesis, that p equals 0.5. That's what the null hypothesis statement was, right? Divided by the denominator will be square root over p sub 0 is this 0.5 value, so 0.5 times 1 minus 0.5 divided by 1015. So 0.53 minus 0.5 is 0.03 divided by, when we do the calculation of the denominator, all right, this here, when we do this calculation, we come up with a value of 0.015, all right, 0.015, and which roughly gives us a value of 1.911. That's our Z sub 0 value, the test statistic value. Now we will be taking this test statistic value and using it with two approaches. One is the critical value approach, the other one is the p-value approach in the next slide to arrive at a decision. Now we are on to using the critical value approach, which is step 4, the first part of step 4, which is using the critical value approach. The other approach is the p-value approach. For the critical value approach, we first have to create our cutoffs between the reject region and do not reject regions, and then we have to bring our test statistic and see where it falls, whether it falls in the reject region or in the do not reject region. So let's first draw a figure. Let's first draw a figure that is a normal curve showing our reject and do not reject regions and find our critical values. Now, this is a right tail test because we are trying to show that the majority of people, that means greater than 50%, said that China is the leading economic power. So that means our alternate hypothesis, if you recall, was that P is greater than 0.5. That makes it a right tail test, and therefore the the reject region is going to be to the right side of the curve, and this area associated with the reject region, this is reject null hypothesis, correct? And this area associated with the reject region is an alpha value of 0.05. And the cutoff, which is the critical value, right? Critical value is the cutoff between the reject and On the other side is the do not reject region. All right, do not reject region. The critical value will be that z value which represents the cutoff between the reject and the do not reject region, and that would be z of 0.05. Right, now if you look up your table, you will find that the z of 0.05 is 1.645. It's 1.645. The good thing about chapter 12, the study on proportions, is that all the inferential studies will use the z distribution. So we will be using the z table for whether we are finding confidence intervals or whether we are performing a hypothesis test, right? So we have z of 0.05 with a value of 1.645. That's our cutoff. But recall that our test statistic, all right, the test statistic we found in the previous slide with the z sub 0 equals, what was it? It was 1.911, correct? So we see where 1.911 falls. 1.911 would fall to the right of 1.645, correct? It would fall, it's greater than, let me write that, 1.911 is greater than 1.645 in a right tail test. That would be fall somewhere to the right, somewhere here, I don't know, maybe somewhere here. You can show it with a dot, or with a heavy dot or a star, however way you want to show it. And that is definitely in the reject region. So we have to say it falls in reject region, therefore it's going to be, the decision is going to be reject null hypothesis. That means null hypothesis was stating that the majority do not think that China is a superpower. It said that null hypothesis P is equal to 0.5, right? That's what the null hypothesis stating. An alternate hypothesis was saying it was greater than 0.5, and based on the evidence we presented, it shows that the evidence falls in the reject region of the null hypothesis. So the decision is going to be reject the null hypothesis. That means the evidence won. The evidence was strong enough to reject the null hypothesis, to displace it with the belief that no, a majority of people thought that China was the leading superpower, right? So let's go on to the other approach, which is the p-value approach, in the next slide. But we should arrive at the same decision. The p-value approach should give us the same decision, should lead to the same decision of rejecting the null hypothesis. So what is the process of using the p-value approach? In the p-value approach, there's no reject and do not reject regions as in the critical value. For the p-value approach, we begin with the test statistic value. So the test statistic value that we found. So number one step is use test statistic value. All right, let's write that down here. Test statistic z sub 0 was 1.911. Now, because this is all z distribution that we are using, we don't have to worry about DFs and all that. All right. So the test statistic was 1.911. And because it's a right tail test, I'm going to draw a figure to explain what we are looking for. Remember, p-value is the probability of finding a test statistic value of 1.911, assuming null hypothesis is true. All right, what is the probability of getting an evidence of 1.911, assuming that the the majority of the people do not think that China is the leading power. All right. Now, let me represent that in a diagram, because you will also need to show it in a diagram on the questions in your assignments and on the tests. We have our Z curve here. This is a right tail test. So what we are going to do is, now again, there's no critical value, there's no reject or do not reject region to deal with in the p-value approach. You first show where the test statistic falls on your normal curve. Okay, now over here, let's say this is the point where 1.911 is. We are just showing, given, this is a 0 at the center, we have a a test statistic value of 1.911 based on our sample study. So we have to find the area to the right. All right, why area to the right? Because this is a right tail test. All right, right tailed. Okay, right tailed test. So area to the right, to right. And that is what the p-value is going to be. This area to the right of 1.911 is going to be our p-value. So our region of interest when we find the p-value for a right tail test is area to the right. Keep that in mind, because sometimes students might be a little bit confused. Which area, on which side should I find the area? And keep in mind your Z table, if you're using the table, it will always give you area to the left. So to find the area to the right, you first have to find the area to the left and then subtract that area from 1 to get the area to the right, and therefore find the p-value in this case. Again, because this is a right tail test. If it was a left tail test, it would be the area to the left of wherever your test statistic was. In a left tail test, your test statistic value would be to the left of 0. All right. So let's go ahead and find the area. So find area, let me write that here, what the step that we are performing. Find area to the right of Z sub 0 equals 1.911. All right, and how do we find that area? First, find area to the left. So especially from a table. All right, if you're finding it using your table, area to left of 1.911 is, what is it? Let me look up my table here. It's 0.971. All right, therefore, or let's write that on, the next line. Therefore, area to right is 1 minus 0.971, which is going to be equal to 0.029. So all this represents the first step, the p-value. So this is our p-value. All right, 0.029. That's our p. So p equals 0.029. In the second step, we compare p with alpha. That's where our significance level comes to play and is being used, all right, to take a decision. So compare p with alpha and see if p is less than alpha. If p is less than alpha, reject null hypothesis. If not, do not reject. So is p less than alpha? So what is the p-value we found? Is 0.029 less than 0.05? Yes. Yes, right? Therefore, reject null hypothesis. And that decision agrees with what we found with the critical value approach. All right, so this is a process we use to find to come to a decision using the p-value approach. Again, first bring your test statistic value, find the appropriate area. If it's a right tail test, it would be area to the right. If it's a left tail test, it would be area to the left. If it is a two-tail test, find the area to the right or to the left on whichever side of zero the test statistic falls on, but then you have to double it. All right, you have to double it and then compare with alpha. Right, so now let's go to the next step where we just state our decision. The main bulk of the work is completed, but writing the decision correctly and interpreting it is also very important in completing the hypothesis test. So the decision we arrived at using both the critical value and the p-value approach was to reject the null hypothesis. Reject null hypothesis, and the interpretation should be at the 5% significance level. Always start with the criteria you use, the criteria at which you perform the hypothesis test at the 5% significance level. Now, because we rejected it, that means our evidence was strong enough to overthrow the null hypothesis proportion, right? So at the 5% significance level, the data do provide sufficient evidence, strong evidence. These are some of the wordings you can use. You just use sufficient evidence to conclude. Against, you have to interpret it in context of the problem that we are working on. So you can use the verbiage from the question itself. The question said at the 5% significance level, do the data provide sufficient evidence to conclude that a majority believe China is the leading power? Just use the wording after conclude. All right, it says the data do provide, that means our data was strong enough to overthrow the null hypothesis. To conclude, what did we conclude? That a majority, which is greater than 50%, believe China is the leading economic power. And that concludes the entire hypothesis test. All right, again, interpretation is very important because after all that work, if you're not able to interpret it correctly, then the whole study will not have any value. Again, these are the keywords. At the 5% significance level, there'll be a point assigned to that when grading. Then whether you have stated correctly whether the data do provide or whether the data do not provide, that is important too. In the grading process, do provide sufficient evidence. We will look for this phrase, and then whether you have interpreted it in context of the problem that we worked on to conclude that a majority greater than believe China. So the interpretation itself is carries 3, 4, or 5 points depending on what the study is about. Now this is the third and final section in chapter 12 on the study of proportions, but this one is on two population proportions. Just like in chapter 10 we talked about the study of two population means, we are now going to study two population proportions. So whenever we talk about two means or two proportions, that means we are comparing the two proportions. So here again, we will end up comparing two proportions. That's what the study will entail, two proportions. And when we compare, that means we look at the difference between the two proportions, difference between two proportions, two proportions. All right. So here we present comparing two population proportions with independent samples. So inferences of two population proportion compares and decides on proportions from two independent samples, but we are studying the same specified attribute. Remember, when studying proportions, we are looking for a particular attribute, a specified attribute, and we try to find from a survey how many or what proportion of the respondents meet that attribute versus what proportion does not meet that specified attribute. Now, when we are working with two population proportions, we are still looking at the same, at one attribute, however, but it's two populations. All right, two populations. We want to compare with how population 1 compares with population 2. What is the difference in the responses between the two populations, right? Now let's quickly run through the notation that we are going to use, and it's going to be very similar to what we did for in chapter 10 for population means when comparing two population means. The only difference here is that we are working with proportions. Therefore, for population 1, we are going to represent the population 1 proportion as P sub 1 and the proportion from population 2 as P sub 2. As for the sample size, we are going to represent that as N sub 1 and N sub 2. Number of successes from population 1 is going to be X sub 1. From population 2, it's going to be X sub 2. And for sample proportions, it's going to be P hat sub 1 and P hat sub 2 for population 2. And the calculation, the formula essentially is the same as what we used before for one population proportion. However, we have to make sure that we are using the correct X values that pertain to population 1. So X sub 1 divided by the sample size from population 1, and for P hat sub 2 we have to use X sub 2 and N sub 2 to calculate P. So we have to keep the metrics aligned to the population so there's no mix up. All right, so it's very important to work in an organized, clear, neat way so that we have our metrics properly defined, aligned, and so on. Otherwise, we will end up with the wrong values, with the wrong calculations. Now, as with any other inferential study, we first have to look at the sampling distribution um, before we go into the inferential study, because the sampling distribution decides the formula. It helps to build the formula that we are going to use to find uh, our test statistic values and what distributions we are going to use, right? So here it's a sampling distribution of the difference between two sample proportions. Again, because we are working with two proportions, we are comparing them, and comparison means we are looking at the difference between the two proportions, and from the difference, from the result of the difference, we are going to determine whether which one is higher or greater than uh, the other one, or if there's no difference, they're almost the same, and so on. So let's look at what the distribution looks like, the sampling distribution, how the samples are distributed. And in any sampling distribution, we talk about the mean, we talk about the standard deviation, and the nature of the distribution, whether it's normally distributed or whether it's right skewed, and so on. So it says the sampling distribution of the difference between two sample proportions for independent samples, mu of p hat sub 1 minus p hat sub 2. That means the mean of the difference of all proportions is equal to whatever the difference is between the two population proportions. Note that p sub 1 and p sub 2 here do not have the hat. So that means the mean of all the differences between the sample proportions, the mean of the difference of all sample proportions is going to be equal to the difference in the population proportion. So let's read how they have put this, explain this verbally. It says the difference between sample proportions is an unbiased estimator of the difference between population proportions. The standard deviation of the difference is given by this formula, the square root over p sub 1 times 1 minus p sub 1 divided by n1 plus p sub 2 times 1 minus p sub 2 divided by n2. All right, so again, this is the standard deviation for population 1. All right, p sub 1 times 1 minus p sub 1 divided by n1. We saw something similar when we were working with one population proportion, but because now we are working with two populations, we have to combine them. So we have p sub 1 times 1 minus p sub 1 divided by n1 plus the p sub 2 standard deviation also, and then the square root of all that. And the difference is approximately normally distributed for large sample sizes N1 and N2. All right. So given that we have this sampling distribution, we are going to see this formula, all right, you can expect to see this formula in the inferential studies we perform. So let's look at this example on performing a hypothesis test for two population proportion. Again, this example is from the book, from the textbook, but let's go through it first, and then also we'll work this through on in our worksheet, right? So it'll be a double practice for you. Okay, so it's about eating out vegetarian. Zogby International surveyed 1,181 US adults to gauge the demand for vegetarian meals in restaurants. The study polled independent random samples of 747 men and 434 women. Of those sampled, 276 men and 195 women said they sometimes order a vegetarian dish when they eat out. We want to use the data to decide whether the percentage of men ordering vegetarian is smaller than that of women. All right, so let's try to think what the study is about. They are trying to find whether men order vegetarian dish more frequently at a restaurant than a woman, or whether they order less frequently than women do, or if there's no difference between the frequency of ordering vegetarian dish between men and women. So here we are talking of two distinct populations. One represents men. We'll put men in population 1. You can put women in population 1 as well, but just for the sake of it, let's put men, because that's how the book aligns men being in population 1 and women being in population 2. Now, the total number of US adults surveyed was 1,181. That will represent our total N. All right. So, N is the total number of US adults. It includes the men and the women. And here it says the study polled independent random samples of 747 men. So out of the 1181 US adults that were polled, 747 were men and 434 were women. That means N1 represents 747 men and N2 are there are 434 women in the survey, so that represents N2, sample size 2. Of those sampled, 276 men, so that means of the 747 men, 276 men said they sometimes order vegetarian dish. So the specified attribute we are looking for is did they order a vegetarian dish or do they order a vegetarian dish? That's the specified attribute we are looking for. So 276 men were success. That means they met that specified attribute out of the 747 men, and 195 women out of the 434 women polled were said they order a vegetarian dish. They met the criteria. So we want to decide whether the percentage of men ordering vegetarian is smaller than that of women. So that's going to represent our alternate hypothesis. I'm going to underline this smaller word, smaller than, because that's going to define that's going to help us state our alternate hypothesis. So the first question is to formulate the problem. What is the specified attribute we are looking for? It's ordering vegetarian dish at a restaurant when eating out. That's what we are trying to study. All right, to determine the demand for vegetarian meals, because that way the restaurants can decide how many types of vegetarian dishes they should include in the menu, what the demand is for vegetarian meals, and accordingly they can put those in their menus. The second part says identify the two populations. So population 1 is going to be all US men, population 2 all US women. Now we are going to go ahead and state our hypothesis, which is going to be the first step in any hypothesis test. It says denote and state the population proportion. So population 1 we already stated were the proportion of all US men who sometimes order vegetarian. Now in the previous slide we just defined the two populations. This time we are denoting the two proportions. All right, there's a difference between population and proportions. So, and then P2 is the proportion of all US women who sometimes order vegetarian. Stating the null and alternate hypothesis. The null hypothesis always has an equals in it, and the way we will state it is P sub 1 is equal to P sub 2. There's no value. The P sub 2 is also a variable. All right, you should not have a constant value, a null proportion value in your null hypothesis statement when working with two proportions, just like it was when we were studying two means. All right, it was mu sub 1 equals mu sub 2. This time we have P sub 1 equals P sub 2. So what does the null hypothesis say? It says the percentage of men is not less than that of women. That means men and women order order vegetarian dishes with the same frequency. The proportions are the same. For alternate hypothesis, it says here we wanted to study whether men order less frequently, therefore whether the percentage of men ordering vegetarian is smaller, and that's the reason we have the less than sign in the alternate hypothesis statement. It says P sub 1 is less than P sub 2, that is the percentage of men is is less than that of women. So I'm going to correct that, okay, in the slide, but I'm going to for now cancel the not. It doesn't make sense otherwise. All right. It should say, read, the percentage of men is less than that of women. That's what the alternate hypothesis is trying to assert. Now, just like in the study on sample means to population means, remember we had the pool test and the non-pool test. Here too, when studying two population proportions, we can pool our proportions into one by combining our x sub 1 plus and x sub 2. So x sub 1 plus x sub 2 divided by n sub 1 plus n sub 2 is our pooled proportion, pooled sample proportion. And we are going to use that in our formula to find our z value in the denominator. So z is going to be equal to p hat sub 1 minus p hat sub 2 divided by square root over p hat sub p. All right, that's the pooled proportion. So we have to do this calculation to use in the denominator of the z value. All right, now we could have actually written this as, I don't know why the book separates these two radicals, but it's the same as saying p hat sub 1 minus p hat sub 2, and we can put the entire denominator under one radical. All right, p hat sub p times 1 divided by n1 plus 1 divided by n2. All right, it should give the same answer. So these are the steps in performing a hypothesis test for two proportions. Assumptions are it should be simple random samples. That goes without saying. It has to be independent samples. And the third one is the one that is different from normal assumptions. That's x sub 1 n1 minus x sub 1, x sub 2 and n2 minus x sub 2 should all be greater or equal to 5, are all 5 or greater. So these three assumptions need to be fulfilled in order to go ahead with the hypothesis test using the Z procedure. Step 1, the way we state our hypothesis, the null hypothesis must always say P1 equals P2, and it should use the population notation. All right, no p hat when stating the null hypothesis or the alternate hypothesis. It should say P1, the population proportion is going to be equal to population 2 proportion, is what the null hypothesis is going to state. An alternative hypothesis can be any one of these three. If it says not equal to, that means we want to assert that the two proportions are different. It's going to be a two-tailed test. If it is less than, then it's going to be a left-tail test, or if it's greater than, it's going to be a right-tail test. In step 2, we decide on the significance level alpha. In step 3, we find our test statistic, but the formula is this. Again, all your formulas will be provided to you in a formula sheet for your tests and exams, so you can always look that up. But just familiarize yourself, because all the formulas will appear together in your formula sheet. You should know which one to use. So whenever you're working on your homework, or whether you're preparing for a test working on a review question, have your formula sheet printed out so that you can, just refer to it. You will have the same formula sheet. It's up there on Canvas. You can download that and get a printout and use that. All right, you have to familiarize yourself, otherwise you'll feel lost in the test, even if the formula sheet is given to you. Okay. So here we have the formula given to us. Again, p hat sub p goes by this formula, x sub 1 plus x sub 2 divided by n1 plus n2, which is a pooled sample proportion used in the denominator of the equation. Step 4 is using one of the approaches. Well, you can use both approaches. The critical value approach is the first one, p-value approach is the other one. You have to define your reject, do not reject region, find a critical value in step 4. And for the p-value, you have to find the probability of getting a test statistic that we found in step 3. If it's a right tail test, the p-value appears to the right. If it's a left tail test, the p-value is the region or the area to the left of wherever your test statistic value lies on the curve. And if it is a two-tail test, all right, just find the area to the left or right or whichever side your z value falls. All right, and then double it. Okay. In step 5, we take a decision whether we reject or do not reject the null hypothesis. So if using the p-value approach, if p is less or equal to alpha, we reject the null hypothesis, otherwise we do not. And for the critical value approach, we check in which region our test statistic falls and accordingly take a decision. And finally, step 6 is interpret the results, and it's last but it's not the least, because it's very important to state the interpretation correctly. All right. Now that we have gone over the steps for the hypothesis test in the last 2 slides, let's get on with this example that we started talking about eating out vegetarian. So we want to decide here whether the percentage of men ordering vegetarian is smaller, less, right? I'm going to underline that, than that of women. Right, and what was our data? It's a Zogby International surveyed 1,181 US adults. That was the total number of people, men and women put together. N equals 1181. That's N without any subscripts. To gauge the demand for vegetarian meals in restaurants, the study polled independent random samples of 747 men. So that was the total number of men in the survey, and 434 women. And these two values should add up to the 1181 number. All right. Of those sampled, 276 men and 195 women said they sometimes order vegetarian dish. And based on that data, we will have to determine whether men order less frequently than women. So first step is to note down the data. N is 1181. All right, and we will have to note down more than what they have asked here, but let's go step by step. Now, what's P sub 0? All right, so P sub 0 well, it shouldn't be P sub 0 really. At this point, it should be P hat sub P. Okay, and we will get to that. All right, P hat sub P, but we will also have to determine some of the other samples. So what I'm going to do is I'm going to just move on, and in the later slides I'm going to do more of the calculations of the sample proportions, because there will be P, not only P hat sub P, there'll be P hat sub 1, there'll be P hat sub 2, and so on. All right, but we're not first going to list our data. check assumptions. Let's check for the assumptions. It has to be simple random sample. It has to be independent samples, independent. And the third one is the important one because that's distinct to this particular study. That's n sub 1 and n sub 1 minus, sorry, I should really say x sub 1. That was misstated. X sub 1 and n sub 1 minus x sub 1. So x sub 1 is 276 men, right? N sub 1 minus x sub 1 is 747 minus 276, and n sub 2 and again x sub 2, I'm sorry. X sub 2 and n sub 2 minus x sub 2, they should all be greater or equal to 5, which clearly it is. All right, so it meets all the assumptions. Then it's a state null and alternative hypothesis. So the null hypothesis will state that P sub 1 is equal to P sub 2. Alternate hypothesis will state P sub 1 is less than P sub 2. And keep in mind there's no hat over the P's when stating the null hypothesis and the alternate hypothesis. Why did I put a less than sign? Because from the question, all right, you have to look for how you're going to state your alternate hypothesis in the question itself. It says we want to decide whether the percentage of men is less than, smaller than that of women. Decide on the significance level. Alpha is 5%. Does it say here? No, it doesn't say here, but we are going to use 0.05 or use the 5% significance level. It'll probably say stated somewhere later in perhaps the next slide or the one after that. All right, but these are some of the basic things that we start with to formulate our problem. Now this is the part where we calculate our test statistics. So I'll just call this z sub 0, and we have to do a lot of other calculations also because we don't have the values for p hat sub 1, p hat sub 2 and p hat sub p. If you remember, we skipped that in the last slide, but I wanted to do everything together here so that you have the values in front of you when plugging into the equation. All right, so I'm going to spend some time to come up with these values of p hat sub 1, p hat sub 2 and p hat sub p. If you recall, p hat sub 1 goes with the formula x1 divided by n1. So 1 represents population 1, correct? So population 1 is men. That's how we formulated this question, this problem. So we have to take n sub 1 is the sample size of population 1. So men were in population 1, therefore n sub 1 is going to be 747. So I'm going to write 747 for n1 and x sub 1. How many men said yes to the question? 276. So that's our x1. So I'm going to put 276 for x1 and we will come up with a value of p hat sub 1 value of 0.369. All right, that's our p hat sub 1. I'm going to write that here. P hat sub 1 is 0.369. We have to do the same thing for p hat sub 2. So p hat sub 2 is going to be x sub 2 divided by n sub 2. So x sub 2 is, what is the total? Well, let's first plug in for n sub 2. 434 women were the total number of women who were in the pool of adults surveyed. So I'm going to put 434 for n sub 2, and x sub 2 is 195 women said they order vegetarian. So 195 divided by 434 is 0.449. 0.449. Okay, so it's p hat sub 2 equals 0.449. We have to then find p hat sub p. So what is p hat sub p? P hat sub p is x1 plus x2 divided by n sub 1 plus n sub 2. So x sub 1 plus x sub 2 is just a second, is 276 plus 195, so that's 471. All right, it's this here. 276 plus 195 is x sub 1, and this one was x sub 2. All right, we add them, and n sub 1 plus n sub 2 is our n, right? This is our n. This is n. So 1181. For a value p hat sub p, value is going to be, that proportion is 0.399. 0.399. So these are the values we will be using in our formula. So z sub 0 is going to be p hat sub 1 0.369 minus 0.449 divided by the square root over p hat sub p is 0.399, right, times 1 minus 0.399 times 1 divided by n sub 1 is 747 plus 1 divided by 434. Okay, that's n sub 2. And when you do this calculation, you should come up with a value, z sub 0 value of minus 2.726. All right, so that's going to be our test statistic value, negative 2.726. That's the difference. All right, and that's a z value of the difference between the proportion, sample proportion between men and women ordering vegetarian food. Now let's perform the test using the critical value approach first. But before that, I'm going to write the value of the z value of our test statistic, and let me use a different color. Z sub 0 that we found was negative 2.726, and also this was a left tail test because our alternate hypothesis said that P1 is smaller than P sub 2. Men order less frequently than women. All right, now this being a left tail test, our reject region is going to fall to the left. So let's draw a diagram showing the reject and do not reject regions and find the critical values. So here is our curve, and this is going to be the reject region, and this is going to be all our alpha value, and we are performing it at the 5% significance level. Let's just use the 5% significance level for the heck of it. So this is going to be alpha equals 0.05. So we have to find our critical value, the cutoff between the reject and the do not reject regions, right? And because it's on the negative side, because it's a left tail test, right? Our 0 is at the center and reject is on the left hand side. The cutoff critical value will be negative z of 0.05. Okay, so the way we are going to write out our findings from this approach is first state what your critical value is. Critical value is negative z of 0.05, which is negative 1.645 if you look up the table, or if you're using your calculators. That's our cutoff. So it's negative 1.645, negative 1.645. That's our cutoff. Now we bring our test statistic value of negative 2.726 and see where it falls in our diagram. Negative 2.726, we see negative 2.726 is less than negative 1.645 and falls way to the left. Somewhere here probably. Negative 2.726, which is clearly the reject region. So we have to say it falls in the reject region. Therefore, reject null hypothesis. All right, we're going to reject the null hypothesis, but before that, let's work this out using the p-value approach and see if we arrive at the same decision of rejecting null hypothesis. Now for the p-value approach, again, we start with our test statistic value, right? So again, let's write our z sub 0 value, that was negative 2.726. So we take our test statistic value and find the area. Now again, because this is a left tail test, the p-value will be the area to the left of wherever the test statistic falls in our diagram. All right, so find area to left corresponding to z sub 0 value of negative 2.726. So I'm going to draw my curve once again and show where negative 2.726 falls on the curve. It's way to the left of wherever the center point is in the picture, and I'm going to raise it. So that's, let's say that's where negative 2.726 is, and this small area, this area is going to be our p-value. It's not the reject region. All right, there's no reject and do not reject regions when it comes to p-value approaches. You just take your test statistic, show where it falls on your diagram, on your under the normal curve, and if it's a left tail test, find the area on the left hand side. If it's a right tail test, find the area to its right, and if it's a two tail test, find the area on whichever side it falls, whether to the left. If it falls to the left of 0, find the area to the left. If it falls to the right of 0, the test statistic, find the area to the right, but double it. All right, multiply that area by 2 for a two tail test, not for one tail test, right? So this is area to the left. We can look up our table and get that area. We don't need to subtract it from 1. That we need to do only if it is area to the right, correct? So here we just need area to the left, and if you look up your table, you will come up with area to the left of minus 2.726 is a very small area, because 2.726 is almost close to 3, negative 3, right? So 0.0032 something, maybe 321. All right, that's the p-value. This area here is 0.0032. 0.0032. So we compare it. Now that we know our p-value, we compare p and alpha. So the question we are asking is p less than alpha? P is 0.00321, is indeed less than 0.05. So yes, it is less. Therefore, reject null hypothesis. And that agrees with what we found using the critical value approach. All right, so now that we have performed our two approaches, we performed the test using both the approaches, we've come to the same decision, we can just go ahead and state our decision and then interpret the test, right? So the decision was to reject null hypothesis, and then the interpretation would be at the 5% significance level, 5% significance level, the data provides sufficient evidence, to conclude, and then I'm going to use the same wordings as in the question. What does it say here? To decide whether the percentage, so to conclude the percentage of men ordering vegetarian is smaller than that of women. All right, that's complete interpretation of the hypothesis test we just performed. Now, along with any hypothesis test goes confidence intervals. So this is a confidence interval for two proportions. Again, the same assumptions that we had for hypothesis test. They have to be simple random sample, independent samples, and x sub 1 and 1 minus x sub 1, x sub 2, and then 2 minus x sub 2 are all 5 or greater. Again, broadly, the steps are all the same. We are just using a different formula to find our interval. All right, again, we are using the z distribution, therefore it's z of alpha by 2. All right, and of course step 3 is to interpret the confidence interval.